Hi.
Okay. Well, okay. Okay. You're supposed to. Okay. So thank you for the wait and for your patience, and thank you for everyone who are here, and for those who are at home. Yeah. So okay. So let's start. So I'm going to talk about uncounting subgraphs, and this will be a bit of a reflective overview of some works with Dana. And why actually counting seeds makes more sense if one thinks about it clearly. And hopefully this will become clear soon. So yeah, so for the reason we all gathered here today, most of us gathered here today, celebrating Dana's birthday. And when Oded first asked me if I could help organize the day, along with Reut Levi and Ronit and Clement and everyone, Michal and others, of course, I immediately said yes, mainly because it's a great opportunity to express my love and appreciation to Dana after all these years. I looked up to Dana since day one, and this feeling has only grew over the years. So this was a good opportunity to do that. And the second reason, which is as important, is my fear of Oded, which also started from day one and grew over the years. Sorry, Oded. Yeah, so actually, some of you know it. Initially, I wanted to go to Weizmann Institute, and they have a committee, and they interview. So I interviewed with Oded, and when I came there, Oded was there with Irit Dinur, and I was so scared I couldn't even speak. So Irit said, okay, take a walk, drink some water, come back. Oded said, no, this won't work. Come back another day, rest some. So it was really extremely nice. So I went back home, and I came back a few days later. That time I could speak, but not think, which is actually much worse. Yeah, so I didn't make it to Weizmann. But fortunately or not fortunately, I don't know, depending on whose side you take, Dana has either worse standards or a better screening process. And I ended up with Dana, which was one of the best things that ever happened to me. So I'm really grateful for that turn of events. Okay, so maybe this is a good place to start the technical talk. Okay, I meant to put names there, but I switched order. So these are some of the collaborators we worked through the years. So that's Will Rosenbaum, Yakub Tetek, Salit Moser, Ronit Rubenfeld, Ruth Levy, Amit Levy, Seshadri, and Shankar. So, okay, so some of them have not directly worked with Dana, but will appear in this talk. So sorry about that. Okay, so for the more formal title, I'll talk about counting subgraphs in general graphs in the general query model, but I'll also mention results in bounded arboricity graphs, and then also some sampling results, and then maybe testing, and sometimes also we assume edge samples. So that's ambitious. We'll see what we'll get. Okay, so kind of this area of study that we mostly worked on together was estimating subgraphs in sublinear time. And this result started with Uri Feige's result on estimating the number of edges. And he gave a two approximation for these tasks. And the main insights in his paper are improved Markov bound, and also partitioning the vertices into heavy and light vertices. And this two approximation is actually optimal in the query model that he considered, which was access to uniform vertices. One knows the labels of the vertices 1 through n, and he can choose a uniform vertex in this set, and degree queries, where you can just query the degree of a given vertex. And in this query model, one can see that it's impossible in sublinear time to distinguish these two graphs, right? Because if we only sample vertices, we'll never hit this middle vertex. So we'll always only hit degree 1 vertices, and it's impossible to tell between these two graphs. But the upper one has n minus 1 edges, the second one has n over 2, so one cannot get better than 2 approximation. Okay, so this was the first result. Then came Oded and Dana, and their main insight was that you can actually get a 1 plus minus approximation if you strengthen the query access a bit, the query model a bit. So they also considered neighbor queries, meaning that given a vertex, you're allowed to access one of its neighbors uniformly at random. And which makes much sense in the adjacency list representation model, right? If we have the adjacency list of the graph. And then the technique they used is bucketing according to degrees. And something additional about me and Dana is, okay, I did look up to her from the start, but it was a bit, it took us time to thaw. I think it's because maybe we're too compatible, and so we're both very sensitive and when I feel someone is uncomfortable, I get uncomfortable myself, and I think Dana is kind of the same. So there was a lot of awkwardness in the room for the years. It took a while to get at ease with one another, but I think now we're in a great place. We're very much in sync, and it's really easy to work together, except for this one thing, which is bucketing. So while bucketing works, that's Dana's main claim, I want to argue that it's not worth it. So this is Feige's result, and you see there's this Markov bound somewhere along here, and this partitioning into light and heavy, and then you get this, okay, you get subtypes of edges, but just 4 of them, because just 2 buckets, just light and heavy, so 4. But then Dana and Oded came along, and this is, I think this is the approximating the average degree by them. You see, so if I search for buckets, it's starting to look bad. It's still okay, it's manageable, but it's getting worse. So then the next result was, again, by Dana. Okay, sorry. So this was Dana, Mira Gonen, and Yuval Shavit. Here now the stats. Okay, and their main insight, again, 1 plus minus epsilon approximation. Again, bucketing, but now sub-bucketing. So if we go again back to this result here, we see that things really, they get worse. So I don't know if you see that, that's 43. Oh, you don't see my, let's see. Yeah, you do not see my screen? You do. Okay, so here we have 43 results, which is like, okay, and then you say sub-buckets, and unfortunately it continues on, and this was stars, and then at that point I came along. And at this point it was me, Dana, and Amit Levy. He was a master's student, and again 1 plus minus approximation, heavy light vertices, and of course bucketing. So this will be the last one of these, I promise. Okay, no, that's not this one. Okay, so buckets. And I don't know, that's 90 if you see that, all here. So we still argue about it. Dana's main claim, and of course she's right, because she's always right, this is very annoying, that it works. But it's terrible. So I'm kidding. Of course, it's really very technical, and I think Dana is one of the few people who can hold this technicality in her head together with the intuition and everything. So of course I'm kidding, but I really dislike buckets. So fortunately at that point, Sesh came along. Oh wait, okay, sorry. So this was us happy after solving triangles. Actually, this is us happy somewhere else, but we solved triangles and we were happy. So this is an illustration of us being happy. This took us like 1 year, and it was the first result. And actually, also the headline was, as I said, it was a bit icy at the beginning, and only after 1 year when I actually solved something with myself, not just helping Dana by being in the room and bouncing ideas. So I told her that now that we finished counting all the triangles, I can't sleep because I can't count sheep. I'm vegan. So Dana suggested counting leaves or seeds, which makes much more sense. Little did I know that 10 years later, I'd still be up at night trying to count subgraphs with Dana, but that's the case. So thankfully at that point, Sesh came and saved us, because it's still 1 plus minus epsilon approximation heavy light, but we got rid of the bucketing by his kind of take on things of simulating edge samples. So we got the same result, but for the happy ending, you can see that, I mean, here, this is it, and you see, no buckets. So we're really extremely happy about that. Of course, it didn't last long, and this is the next result. And already the buckets are back because we reconsidered stars, but this time in bounded arboricity graphs, again, 1 plus minus approximation, but now super simple and elegant edge counting. So if the triangle counting, the original one with all the buckets, and it was extremely hard to read. Also the stars one, it's very technical, but I think really this paper does worth reading because super simple and elegant edge counting that generalizes Fager's result and done in no deads, and of course no bucketing. And it really, you see all the intuition. It doesn't hide there in the technicalities, so it's really nice. And we also simplified the star counting for general graphs. Alas, we had to use bucketing for the arboricity, but it's only in the analysis and it's not in the algorithm, so at least we had that. And yeah, so that's kind of a quick overview of how we started working on this area. And again, let me now go into more technical details of one of the results. So I mentioned the arboricity of a graph and that a lot of our results are for bounded arboricity graphs. So the arboricity is a measure of density of the graph. It's the minimal number of forests required to cover the edge set of the graph. Or we can also express it more mathematically formulated as the maximum over all subgraphs of roughly the average degree. So if the arboricity is high, then the graph has some dense subgraph, and otherwise it's kind of uniformly sparse. It's sparse everywhere along the graph. And as it turns out, this could be very useful also in sublinear algorithms. It was known to be useful in many classical algorithms, and in recent years we see it often in many of the models we consider in sublinear time, streaming, and so on. So we also consider this family of graphs, and also it's a very interesting family of graph, a rich one. It generalizes excluded minor graphs, bounded degree graphs, and bounded expansion, and also it is empirically shown that many real-world networks have bounded arboricity, so it can be useful in practice. Okay, and at this point, at some point, I thought I'll give you a review of results, but then it seems terrible. So instead, I think I'll give a technical result, unless someone wants or could maybe ask me later, I don't know. So this is kind of a picture of where things stand in sublinear counting in the general model, and also some in the edge sampling model. But I don't know, maybe I don't know, do you prefer a technical result or is it more of an overview? We can ask the crowd maybe. Okay, not with a terrible table. Okay, that's good. So that's what I heard, I don't know. So now we can just have maybe, so ignore this screen. I don't know. We'll have that, and I'll use the board. Does it? Okay. So maybe I'll just, okay. What will I do with the screen? Just erase it and have a white. Just disconnect? What do I do? Okay. Okay. So I was very nervous. I don't know if you can tell, but I prepared like 3 talks. So you can choose if you want triangle counting or edge sampling. I don't know. Who is for triangle counting? I see 3 hands. Who's for edge sampling? Edge sampling it is. Okay, great. So uniformly sampling an edge. in sublinear time. So, okay, it doesn't go well with the title, but the idea is to show like just two of the techniques that we used a lot in this series of work. So, so first the query model. So it's again the general one, or maybe just the adjacency list. We don't need per query. So we have uniform vertex queries. Just return, like we know, or alternatively, we know the labels of all the vertices and we can access each one of them. And then we have degree queries. Just gives us the degree of the vertex. And finally, as I mentioned, neighbor queries. So they return a unit, neighbor VI. Returns the ith neighbor of V. Good. So we're working in this query model. And what's the goal? So the goal is to design this kind of button that says, sample, give me an edge. And every time we hit this button, we just press it, it returns us a uniform edge in the graph. And what this does is it uses its query access to G to output an edge such that for every edge in the graph, the probability that this edge is the one that is returned is roughly, it's within 1 plus minus epsilon over m. Okay, so we want that every edge is almost equally likely to be the edge that is returned. Okay, so this is L infinity closeness or pointwise closeness, close to uniform, right? So in uniform, this is exactly 1 over m, and we allow just up to 1 plus minus epsilon multiplicative error, close to uniform. Okay. And we should compare this to the most standard distance measure that's usually used in property testing and sublinear, which is L1 closeness, TVD. But there, what we are allowed is for the sum of distances to be at most epsilon. Okay, so when we sum over all cumulative error, we allow epsilon error. But the difference is that here we are allowed to ignore an epsilon fraction of the edges. So if we zero out epsilon fraction of the edges and then we are uniform on the rest, then we'll still be close in L1 distance, but we completely lose track on an epsilon fraction of the edges. So in property testing, this is sometimes okay, or most of the time, because we know there are many violating edges. But in sublinear counting, sometimes we can't allow it. So for example, consider this graph. And say it's kind of, there's just this cycle here. It's very sparse, mostly. This is on n minus square root m vertices. But here there's this click on epsilon square root m vertices, or square root of epsilon m, never mind. Then if I want to use this button to sample edges in order to then get to be able to count triangles, right? If I allow myself to ignore square root epsilon m of the edges, I'll never see any triangle. So it's true that there are very few triangles in this click, very few edges in this click, but all the triangles reside on that click. So even though there are few, they are very important. So in such applications, we cannot, sometimes DVD is just not enough, and we need this L infinity closeness. So that's the motivation. So far, the problem statement, is it clear? Okay, good. So now for the algorithm. I'm gonna erase that part, is that okay? I don't know if they flip or I don't, yeah, okay, I can just do that. Very good, yes. Okay. Okay, so let's start. So let's start with a very easy warm-up. And we'll have a regular graph G. So here's our graph. And let's say that all vertices have degree D, right? So this guy has degree D, and this guy as well, and so on. Okay, so this is degree D. I will erase this. So what do you say? What is the algorithm for sampling a uniform edge? Yes, thank you. I don't know who said that though. Who said it? Okay, thank you. Sorry, I don't hear well, so I never know where sounds are coming from. This is also common for me and Dana, but luckily we fit in the hearing sides, so it works out. Otherwise, we couldn't have worked together. So the algorithm, sample a vertex, right? Basically, that's all we can do, right? What else can we do? Sample a vertex. After the first triangle results got in, so I told about it to some professor, and he said, well, what do? You just sample, right? It's sublinear time, that's all we can do. So we sample, yeah. So here too, we sample a vertex, but then we sample a neighbor. Right? And then what do we get? Okay, good, so that's the algorithm. So, right, so we sample a vertex V, and then we sample a neighbor U in gamma V, uniformly at random. And then what do we get? That for every E, what do we get? The probability of E is just, yeah, I know it's easy, but flow with me, go with me. What's the probability I get E for this specific E, right? This V here. Yeah, it's just like, okay, it's just the probability I get V is 1 over N, right? Then the probability I get U is 1 over D. Also, I'm gonna treat VU and UV as two different edges throughout. So M will be the number of, I call it oriented edges. It's not that they are directed or anything, but I want to think about it as two different edges. It's just kind of like, then I don't have to carry this 2 factor all the time. Okay, so just 1 over N times 1 over D, right? Good, okay, this was easy. So what about if it's not regular, but bounded degree? So bounded degree, and we have D max, right? So now maybe these vertices have low degree, and there's some vertex here, just maybe this one is isolated. What will change? Rejection sampling, good. Oh, I wanted to mention techniques. Okay, good. So rejection sampling, exactly. So I sample a vertex V, I sample a neighbor U, but then what do? I only return the edge. I only return VU with probability dV over D max. Sorry, D max, right? So for each edge, the probability of E, it's 1 over N. Now it's not 1 over D, right? It's no longer regular, it's 1 over dV. But using rejection sampling, you can just do dV over D max. And I get 1 over N D max. So let's see what happened here. At first glance, this seems kind of wasteful, right? I throw away, I see an edge, then I throw it away, which is kind of weird. But it helps us being uniform. And being uniform is important in all of our algorithm and works. It reduces the variance, and I don't know, it helps us know what's going on. So let's see what we lose here. This is the probability for a specific edge. What is the overall probability of success? Probability of success in returning any edge? Yeah, so M and D max, right? There are M edges. Each one gets this probability, right? When I try this, when I do this algorithm, every edge kind of, right, is distributed this probability. So overall, the success is M over N D max. So this means that, right, by just like standard Chernoff or whatnot, like just flips of a coin, I need to repeat kind of roughly N times D max over M many times to get anything, right? This is just a coin that succeeds with this probability. I just need to flip it the inverse number of times. So, okay, so if D max is small, or if the graph is regular, then N D max is M, and we get O of 1. So, we always succeed. if dmax is small, also this is good. If dmax is n, which might be the case, well, then this is just n squared over m, which is kind of the trivial algorithm of just sampling pairs and seeing if it's an edge. It will output a uniform edge, but it's very costly. So our goal is to get to the square root of it, to n over square root of m. Okay, and we'll see how this can be done. And okay, I didn't state the result by Feige, but this is the counting result by Feige, and the rest of these results, it's n over square root of m. So this is optimal. And actually, you can see why. It's exactly due to this hiding click thing, right? So if I hide all my edges on a very small click, unless I make these many queries, I can't hope even to hit a click. But this is also sufficient, and we'll see why. Okay, so now no longer bounded degree, so let's get to general graphs. So, okay, so we're done with the warm-up. Okay, maybe let's just do that. But we've seen that what helped us here is this dmax bound. So we'll actually use that. So as I said, I'll show you a few, I'll mention a few techniques, right? So we've seen one, and it was rejection sampling. The second one would be like making things uniform. It's not exactly a technique, I don't know, but it's kind of, it's a good idea to keep in mind. If things are uniform, it's easier to analyze. Making things. This is actually where buckets come from, right? They make everything uniform. Inside the bucket, all vertices kind of behave the same. But it's terrible, so still don't use it. No, you can use it. It works, unfortunately. And the third thing is heavy light, right? As I mentioned for Feige and for the rest of the results. So we use the first two. Let's use the heavy light. Okay, so I'll define light vertices to be vertices with degree at most square root m over epsilon. And we'll see soon where this is coming from. Heavy ones, well, these are just the rest of the graph. Okay, and then we'll sample them separately. And these are vertices, and I'll also call an edge light if it originates in a light vertex, and heavy if it originates in a heavy vertex. Okay, and then we'll have two separate procedures for each. I'll choose one with each one with probability 1/2. So I'll just choose one, it doesn't matter. Okay, so we already know how this is going to look like, right? How is sample light going to look like? It's actually on the board. Right? We sample a vertex V. Maybe I'll do it here. We sample a vertex V. We sample a neighbor U, right, uniformly at random. And we return VU with probability dV, but not over dmax. What now do we do? Yeah, this is root m over epsilon, this threshold. Of course, this doesn't make sense if dV is greater than square root m over epsilon, right? So I do need to make sure, like 1.5, if V is not light, then reject, right? But that's okay, because I'm only aiming at sampling light edges. So fine. If it's a heavy vertex, fine, let's throw it out. If it's light, I do this rejection sampling. So what do I get? For every edge, what's the probability? It's exactly as before, dV over square root m over epsilon. Okay? And let's wait with this one, this analysis, which is exactly the same. Let's wait with it until the end. So we get that every edge is sampled with this probability. Okay, so 1 over n square root m over epsilon. Okay, so this was for light, and you see this is an equal probability for all light edges. So far we're good. We're uniform on all light edges, and we're happy. What about these heavy vertices? So let's see where this threshold came from. So I'll do it here. So what do we know? Why is this the threshold? Because we know that m is the sum of degrees in the graph, right? Which is greater than if I sum only on vertices in H. which is greater than h times this threshold, right? Because every vertex in H has the grid least that. So, like very simple kind of Markov-like argument. H is at most m over this threshold, right? It's epsilon. Okay. See, this is hopefully you see that. It's square root of epsilon m, which is epsilon. Maybe it's easier to write. Okay, right? This is just algebra, very simple one even. And now that this is exactly the threshold for being heavy. So, sorry. Right? For every heavy vertex, we got here exactly epsilon times the threshold of being heavy. And for every vertex, heavy vertex, its degree is at least that, right? So we got that for any v in H, dH of v, that's it's like, right? If this is my light and heavy and threshold, if this is some vertex v, its number of vertices of neighbors inside this heavy set, well, it's at most the size of the heavy set, right? It can't have more neighbors than the size of the set. And this is at most epsilon dv, right? The contra-positive of this is that most of its weight, most of the edges of this vertex, most of its neighbors, and 1 minus epsilon fraction of them are coming from light vertices. Okay? So most of the mass of this vertex comes from light vertices. Okay, so this is where this threshold came from. Just this, wanted this m over the threshold to be at most kind of something that relates again to the threshold. So what do you say? How do we sample light and light vertex?
Heavy.
Heavy, thank you. Good. You're awake.
Sample a vertex and then sample its neighbor?
No, we did it already.
No, meaning to think that the heavy would be the neighbor of the light.
Of the light, right? The neighbor, but we know how to sample light, so let's just sample light, right? So let's invoke sample light. So invoke sample light, and this returns an edge, right? We get an edge VU. We get VU. And recall, we get the edge VU. V is light, and U is, we don't know, right? But what do we hope? Right? If we hope that U is, right? We hope that U will be, sorry, so this is U. We sampled some edge VU, and we were hoping that U is our heavy vertex. Okay, so if U is not heavy, we reject, we fail. Because we're trying to get to these heavy vertices. Now we're in sample heavy. But otherwise, we sample, what do we sample? I have a vertex in my head, what can I sample? Neighbor, yeah, that's what I do. Otherwise, sample U, W in gamma U. Yeah, it's really not complicated. It's really there. It's just nice and simple. Just need to look at it the right way. So we just sample a neighbor, and what do we get? Let me do it here. Let's analyze. Let's fix this specific heavy edge and see what's its probability. So for any in this heavy set, what is the probability of it? How can I catch? Let's call it by its name. Right? It's not. We had V and then U, and then we sampled this neighbor. I don't know, say W here. So what's this? What is the probability of UW?
First, you have to sample a light neighbor of U.
Yes. So first I have to sample a light neighbor of U, and I have DL of U many light neighbors, and each, by the previous analysis over there, is sampled with equal probability, exactly with probability 1 over n square root m over epsilon. Okay? And I have exactly d light u vertices. Yeah. Okay. So, and then I go ahead and I sample w. If I did hit u, then I don't reject. And I go ahead and I sample w. So this happens with probability 1 over du. And I get this dlu over du, right? And what do I know about this relation? This is exactly in 1 minus epsilon over n squared m over epsilon to 1 over n squared m over epsilon. Okay? So I get that also heavy edges are sampled with almost exactly the same probability. Okay, I just have this 1 minus epsilon factor. Okay, no, I should say R. This is the R moment. Thank you. Okay, good. So if I go back to this analysis from before, the overall probability of success, it's almost 1 over n, right? It's at least m over, sorry, 1 minus epsilon, n square root m over epsilon, which is square root m over n, roughly. I'm now ignoring epsilon factors, so it means that I need to do it n over square root m many times to get a uniform edge. Okay, so n over square root m, and this is optimal. What's not optimal here is that I ignore these epsilons, but there's an epsilon factor here. And also I don't get exactly uniform, I get pointwise close to uniform. But actually, I have 3 more minutes and it's enough to make it exactly uniform, which is kind of cool, or extremely cool actually. And all I need to do is to see where is the source of error coming from. And the source of error is this dlu, right? For some vertices, it might be 1 minus epsilon, but so maybe some vertices, maybe all of their edges are here, and then it's exactly 1. So I have this discrepancy. But I notice it's a very small one. Say I take epsilon to be 1/2 or 1/4, right? Then I do get that all heavy edges, and only the heavy ones are problematic, right? All the light ones are sampled exactly uniformly. So I have this thing that they're sampled with probability like between, I don't know, 1/2, this n, never mind this thing, right, and 1. Okay. So how do I get rid of this? Basically, what is that? What is this factor, this 1/2? It's this, maybe I'll write it like that. It's this dLV over dV, right? If I could get rid of this factor, right, maybe using what? Rejection sampling, that would be good, right? And then I could, can I hope to get here dV over dLV? This expression makes no sense, right? Why? It's more than 1, but here, now it's all good, right? Because dLV, if I set epsilon to be 1/4, right, then dLV is at most 1/4 of the degree. So now this is larger. Sorry, it's at least 3/4 of the degree. So this now is larger. So we want to sample, we want to do rejection sampling with this probability. But actually, how can we do it? We don't know the light of V. So we can try to estimate it, but that will give us an estimate, so still an error, and also it will cost us 1 over epsilon squared. What's nice that we actually don't have to estimate it to reject by this probability. We have access to a coin that succeeds with this probability, let me call it P. Right? If I just sample a neighbor of V, and I check is it light or heavy, I just do a neighbor query and a degree query, then this is, and if it's light, it's heads, then I have a coin P that succeeds with this probability, with probability dLV over dV. And then I want to reject with probability 1 over 2P, right? But fortunately, this is solved. So someone already solved this problem, given access to one random coin. How do I simulate access to a different random coin? So given access to P, which behaves nicely in some way, there is a simulation by, now I forgot the name, I'm sorry. I'll get back to you on this. I can simulate a random coin with probability 1 over 2P. And then I am done, because then I have this rejection sampling, and I get that all heavy vertices are sampled with probability exactly 1/2n square root m over epsilon. I go and do some rejection sampling there with probability 1/2, and I'm done. I get that all edges are sampled with exactly equal probability, and all it costs me is this additional simulation, but also fortunately, this is O of 1 in expectation. So that's it. So get an exactly uniform edge in optimal time, and this is a result by Yakub Tetek and Shyam Nayaranyan. And yeah, thank you.
So is there any question for Talya? While the next speaker, surprise, it's going to be Arthur. We're still trying to figure out the Zoom situation, so the Zoom talks are going to be a bit later. So the next talk is going to be by Arthur on testing networks that compute.